Okay, so we're going to learn horizontal projectile motion. It's basically where we have a projectile, maybe a car, maybe a ball, being thrown or driven in a horizontal direction. So you'll notice that it has a horizontal velocity at the beginning. Okay, it's going to make some sort of shape like this until it reaches the bottom, and a little crash. Okay, so my question is, what was the velocity of the car when it left the cliff? So as we look at the car and we watch its path, we know that it's changing in two different dimensions. It's changing both in the x dimension and the y dimension. So it's traveling this far in the x direction, and it's traveling this far in the y direction. So those are two things that we're going to be given. It is a 30-meter high cliff, and it falls 20 meters away from where it originally started. So in order to do our givens, we're not just going to have x's or y's. We're going to have two sets. So we're going to have our x knowns and our y knowns. Okay, so same thing we've been doing with kinematics so far. We start listing them out. V initial, V final, acceleration, delta D, and time. And for the y's, V initial, V final, acceleration, delta D, and time. So the first thing we want to do is we want to start putting down all the givens that we know. Okay, so we know that it's going to be 30 meters below where it started. So that's a change in the vertical position, so that's negative 30 for the y. It's going below where it started. And the x, it's going further to the right than where it started, so 20 meters is positive, 20 meters. So if we want to put subscripts on this, delta dy, delta dx, so we know for sure, ay, vfy, the initial y. Okay. So there's a few other things that we know. So let's look at the y scenario. So as the car is falling, it's experiencing an acceleration in the y direction due to gravity, so negative 9.8 meters per second squared. We also know that its initial velocity, it only has initial velocity in the x direction. It doesn't have an initial velocity in the y direction. So that's going to be 0. Okay. In order to figure out a few more knowns, so we have 3 here, but we only have 1 in the x. So our ultimate goal is to find v initial x. So we're going to need another known up here in the x's. So if we look at the motion that the car makes, so as it's traveling further and further down, after it leaves the cliff, there is nothing affecting its acceleration in the x direction. If the person in the car puts their foot on the brakes, it's not really going to stop them. They're still going to continue traveling in the same path. If they put their foot on the gas pedal, they're still going to continue traveling in the same path. So really there is no acceleration in the x direction. So this is 0. Okay? There is something we know that is the same about both of these. It's the time. So time does not change depending on the x or y direction. So both of these values are equal. So if we find one, we can find the other. We have 3 knowns on this side, so that means we are able to find an unknown. We can find time. So we're going to use the equations. Let's use our y's. Our equation delta d equals VOT plus 1/2 AT squared. Now you'll notice I didn't put the subscripts y down because I said we're using the y's right here. We want to make sure that we don't interchange these knowns. So don't just plug in a is 0. We have to make sure we're only using the y's. So delta d for y is negative 30. The initial is 0. T plus 1/2 negative 9.8 t squared. So this cancels out. You get negative 30 equals negative 4.9 t squared divide by negative 4.9. When you solve, go ahead and solve, take the square root. You should get 2.47 seconds. So there's our time. Knowing that, we can plug it back into our givens. So we know that's y and it's the x, because time doesn't depend on whether you're in the x dimension or y dimension. Okay, well now we have three knowns. We can solve for our unknown, our v initial in the x direction. So let's go ahead and do that. So we're going to use the same equation that we just used. Delta D equals VOT plus 1/2 AT squared. So 20 equals VOT plus, actually let's just cancel this out right now. So this is 0 because A is 0. A is 0. Okay, so we get 20 equals V initial times 2.47 seconds. Solving, you should get V initial equals 8.10 meters per second. This is the x initial velocity. So let's go ahead and plug that back up into our knowns. 8.10. Okay. So the next thing, I'm going to ask you a follow-up question. Here's the follow-up question. How fast was he moving on impact? So when he hit the ground, how fast was he moving? Well, if we go back to our picture, you'll notice that here's the V final. The V final is right here. It's in this direction. So that means it has a y component and an x component. I'll draw that a little bit bigger down here. So he finishes, here is the V final. It means he has a y V final and an x V final. V final x, V final y. Okay, so we just found the V final x. Well, no, we didn't find the V final x. Let's find the V final x. So intuitively, we can actually think about this. If we look up at our knowns for the x direction, we know that his initial velocity is 8.10. And we know he has no acceleration. So if an object has 0 acceleration, that means they have a constant velocity. So it stays the same the entire time. So this should be 8.10. But if you need to use an equation to verify that for yourself, please do. This is the equation you should do. VF equals VO plus AT. You get VF equals 8.10 plus 0 times 2.47. This cancels out, so there is your VF. Oops, sorry. Okay? So now all we need is the VF in the y direction. So we had acceleration in the y direction. Our acceleration is negative 9.8. We also have the time, 2.47. And we have the V initial in the y direction. So essentially we can find VF in the y direction. VF equals VO plus AT. Plug that in your calculator. You should get V final is equal to negative 24.2 meters per second. Okay, there's our y component. And now we just need to be able to find, so now that we have V final y, we have V final x, we can find V final using the same methodology you learned previously in vectors. So there's our theta, because we will also need direction. I'm going to redraw my little triangle. So So this is 8.10. This one's 24.2. Here's theta. There's V final. That's our question. So we can use Pythagorean theorem to find V final. So VF squared, since it's the hypotenuse, it's going to be equal to 8.10 squared plus 24.2 squared. That negative doesn't really matter because once you square it, you get a positive. So you get VF is equal to the square root of 8.10 squared plus negative 24.2 squared. Make sure you're actually practicing this on your calculator right now. So if you need to pause the video, please do. VF is equal to 25.5 meters per second. Okay, well that's not enough information. Knowing that this is 25.5 meters per second is great. That's only the magnitude of the velocity. We also need the direction because velocity is a vector quantity. Vectors have magnitude and direction. So here's our magnitude and we need our direction. So at some angle. So that's what we need to find next. Well, we know, remember we always use tangent when we know the x's and the y's. So we're going to use tangent. Tangent theta is equal to opposite, which is your x, over adjacent, which is your y. You get tan theta equals 8.10 divided by negative 24.2. You get theta equals arctan 8.10 over negative 24.2. Plug that in your calculator. Get theta equals negative 0.5 degrees. The negative is just telling us that it is below our horizontal line, but we don't really need that information because we're going to give that information the direction by stating our cardinal directions. So we are going south of or east of south. So we're starting out going south and then we go east. So we're going east of south. East of south. So let's add that information up here. 18 degrees east of south. It would be equally correct if you said the theta was, if you found this theta instead right here, and you said it was, let's see, 90 minus 18.5, you'll get 71.5 south of east. So those are both correct. Both of these are equally correct. Okay.